Hello everyone. In this video we are going to talk about predicates and quantifiers. So first we'll just define a predicate, right? So it's a statement p of x that incorporates some variable x, and whenever we put in an actual value for x, the result is a proposition, and so is unambiguously true or false. So I want to make a couple of notes here. So first, predicates can take in more than one variable. So just a quick example, you could have like p of xy mean x is friends with y. Right, so that's obviously a real world example, but this would include two variables, and you can imagine going even more than that. But most of the things we'll deal with will have one variable. And then second, the variable x will come from a specified domain, right? So you might say like x has to be a real number, or x is an even number, or if you're talking about x is friends with y, you might say that the domain, your x and y, have to come from people from our class or something like that. Okay, so these are examples of domains, and so you want to make basically your context clear before you actually talk about your predicate. So we're going to come back to that notion of domain a bit later when we talk about quantification. But first, let's just do an example here with a pretty simple predicate. So just the statement x is greater than 0, and here I am just going to say that the domain is R, or the set of real numbers. That's just the symbol we use for that. And again, once we specify a value for x, it should become a proposition, right? So let's just look at three different values real fast. So -7, and 0. So if I plug in 2 here, it says 2 is greater than 0. Well, that's true. -7, that's not greater than 0, so that's false. And 0 is also not greater than 0, right? It's equal to 0, so this would be false. And this kind of leads naturally to the notion of negation. So one can negate predicates as well. So if we negate p of x, right, this would be not p of x. We could write it like that. And this would just say not greater than 0, which is the same as less than or equal to 0, right? That it's not positive. And of course, for all of these, we just flip, right? So if x is 2, this becomes false. X is -7, it's true. And 0, it's also true. And so matches what we would think would happen for a negation. So let's do one more quick example just to, again, kind of re-emphasize De Morgan's law. So here my predicate is x is less than -2 or x is greater than 2, where x is a real number. So one way you could think about this is going to be true specifically for the numbers in these intervals, right? So kind of the thickened part here, but not including -2 or 2. Okay, so then how would we negate this? Well, this is De Morgan's law, right? So to negate an or statement, we would then get not x is less than -2 and, right, that one switches, not x is greater than 2, or equivalently, we know what this means. This is saying x is greater than or equal to -2 and x is less than or equal to 2. So basically the first one corresponds to the dark and black part, and then the red part, and now including those endpoints, is where the negation is true. Okay, and so here's your first exercise. So given this p of x, where my domain is the real numbers, and by the way, this little epsilon here just means is in. So you could, or is an element of. So you can read that as x is in the real numbers. So the first part, I just want you to give examples where the predicate is true or false. And then I want you to write down the negation. So now we're going to look at quantifiers. And this is going to kind of stem from this question here. So given a predicate, call it p of x, is this predicate true when replaced by values in the domain? It's a pretty natural question to ask. And I'm going to give what might seem like a somewhat unsatisfactory answer. The answer is either always, sometimes, or never. It seems like that should be pretty clear, but let's think about some examples of each. So here I'm going to consider p of x to be x squared is greater than or equal to 0, again, where x is a real number. This is always true, right? It doesn't matter what real number I plug in. If I square it, it's always going to be non-negative. So that's always true. So q of x here, I'm going to have x squared greater than or equal to 4 for all real numbers. Now this is just sometimes true, right? Because this is definitely not true, for instance, for 1. But this is where domain really matters, right? So if x is a real number, this is sometimes true. But what if I change it to x is in the interval from 5 to 10? Well, then suddenly it changes to always true, right? And so you really do want to consider what domain you're working within, because it might change the truth value of your statement. And lastly, one that's never true, well, we can just take the negation of something that's always true, right? So r of x, or you could just call it not p of x here, would be x squared less than 0, right? It doesn't matter what number you plug in. If you square it, it's not going to be negative. Okay, so now we're going to look at the two quantifiers that we're going to talk about here. So the first one looks like an upside down capital A. It means for all or for every. And so once we slap a quantifier on a predicate, it becomes true or false. So let's look at an example. It's actually going to be one of the ones we just saw, basically. So for all x in R, so for any real number, x squared is greater than or equal to 0. Right? So if you just look at this part, this is a predicate by itself. This quantifies the predicate. So this becomes a quantified predicate once we slap on the for all out front. And now it's either true or false, right? So this is saying for any real number you choose, x squared is greater than or equal to 0. And this is true, right? But I could say, for instance, for all x in R, x squared is greater than or equal to 4, like that second one, right? That one was sometimes true. And so this is saying for all cases, it's greater than or equal to 4. This is false, right? How do you show that a for all statement is false? You just need one counterexample. Of course, here we have plenty of counterexamples, but all we need is one. Say x equals 1, right? 1 squared is less than 4. And so that's a counterexample, and it proves the falsehood of this universal quantifier, the for all statement. So now we're going to look at what's called the existential quantifier, and it's called that because it basically means there exists. And when we say that, we really mean like there exists at least one such that something is true, okay? So for example, there exists an x in R such that, I don't know, x squared equals 0. Is this true? Yeah, this is true, right? And all we need is one example, and luckily all we need is one because there only is one, right? X equals 0 makes this true. However, if I say there exists an element of the real such that x squared is less than 0, this is false, right? We have no numbers that we can pick as an example where if you square it, it's going to be negative, right? So there are no examples. And thus, nothing exists. This statement would be false. And for your second exercise here, I'm going to limit the domain, so no longer just the real numbers. You're only considering the values, so x values from 3, 4, 6, 8, or 9. And I want you to look at these 4 quantified predicates and determine whether they're true or false. And if they're false, explain why. Thank you for watching.